that comes into play with those sorts of things. It's really actually pretty exciting stuff, because when you start thinking about like functions in two-dimensional space, it's got value, but the best you can do is just kind of imagine what it would look like in three dimensions. But now what we're going to do is learn the different ways in which we can manifest certain curves, surfaces, and all that good stuff in three dimensions and beyond. Right. So it's definitely a different form of math, but with familiar aspects to it. Right. And then when you start thinking about the fourth dimension, you know, I always cringe when people say, the fourth dimension, time. I'm like, that's sci-fi. The fourth dimension is a fourth variable. Right. So if we're looking at the physical world with the length, width, and height as being the first three dimensions, which isn't necessarily the case, because the first dimension could be time, the second dimension could be dollar value, and the third dimension could be age, you know, time passed in terms of an investment, you know, maturity level of an investment, you know, things like that. These are all things that could come into play as variables. It's just three variables. But if we're talking about the physical world, then we could say length, width, and height are the first three dimensions. Most people agree with that. But the fourth dimension may not necessarily be the passage of time. It could be the temperature. Right? So if you have a particular location, you're within a room, and you look at the lower corner, you know, where the walls and the floors intersect, or the walls and the floor intersect. And that one corner, you know, you have four corners. One corner you designate as the origin, and you relate every point back to that one location, creating a vector value function. Then your position within the room would also have a relationship with the temperature or the pressure within the room. So, I mean, if I want to get temperature and pressure, now I'm up to 5 dimensions. Now, if I want to do that over time, I'm up to 6 dimensions. And so every time I incorporate a variable, I'm including a dimension. The problem is we think at best 3-dimensionally. Most people think 2-dimensionally. The best we can do under most circumstances, you know, on average, humans, is think 3-dimensionally. And very rarely does a person tend to think 4 dimensions at a time. Right. So, but there are people who can do it. I mean, actually, lots and lots of people who can do it. The more variables you throw in there, the harder it becomes. So that's what we're going to investigate. It's really very interesting, fascinating stuff. So, but we got to start from the basics. Right. So what do? We learn how to evaluate a function. We learn how to find limits. We learn how to determine if a function is continuous and what it means to be continuous under those circumstances. Then we get into derivatives and antiderivatives. And then we start doing the applications of those things. So basically, it's Calc 1 all over again, because now we're incorporating other variables within our functions. All right. So for number 1 here, we have this multivariable function that's written as f of x comma y. That's the kind of thing. I mean, I have all these notes up here that you can read through, but most people look at this f of x comma y and say, oh, okay, it's like f of x, just I'm throwing another variable in there. All right, I'm with you. If I said f of x comma y comma z, I'm throwing in an additional variable, right? X, y, and z. Right? If I had f of x comma y comma z comma alpha comma beta comma, you know, all that stuff, then you would expect to have all of those variables within your function. Whatever you're stating here within your notation, you are designating officially as a variable within the function. Anything else that's represented in there is assumed to be constant. So if I have some a value, so if I have the letter a in there, that's assumed to be constant because it's not one of the two functions that, not one of the two variables that define the function. Right? That's all stuff that we're used to. So what we want to do is find the domain. So what do? We look at this function one variable at a time. Because I'll tell you, you don't want to be doing it by necessarily, sometimes you can get away with it, but you don't always want to be doing it by looking at the graph. And I'll bring up a GeoGebra real quick. And then, I'll bring it up real quick and then spend 17 hours trying to make it work. But what we can do, if we think of f of x in 2 dimensions, we define that as y equals. We can think of f of x comma y as z equals. So this is the same as saying, the same as z equals y times the natural log of negative x. All right. So it's really just kind of begging the question, why are we allowed to call that z? And I could easily just say, well, the same reason we were able to call f of x y, or the same reason we were able to call f of y x, which is, of course, not an explanation. All right. So if we're working in 3 variables, all right, so we're working in 3 variables, and I'm saying that one variable is going to be a function of another 2, depending on what those other 2 variables are. Again, this all comes down to, if I can actually draw a diagram, as you know. And you know what, honestly, I think I mentioned this enough. I've been teaching about 20 years. Next year I won't talk about as much how many years I've been teaching. It's just kind of like a milestone. So over the course of the 20 years, when they do those mid-semester surveys where they talk about how awful the teacher was or how great they were, nobody's ever said anything about how awful my diagrams are. Right now, this isn't too bad, but I got a lot of help here. It would be fair game. That would be it's not constructive criticism because I can't do anything about it, but that would be a fair critique. Like, hey, he's a pretty good teacher. He's a pretty nice guy. Can't draw to save his life. That's self-reflection right there. I admit it. That's pretty bad, which is why I don't require you all, to provide artistic work on assessment. Anyway, so if I'm telling you that you have the x-axis, the y-axis, and the z-axis, you're going out a certain distance in x, a certain distance in y, and we're thinking about perhaps, maybe that gets you to this location, for example. We're thinking about, okay, well, where else is there to go? We've already traveled in the x direction. We've already traveled in the y direction. The only place left to go would be either up or down. So whatever value you get out of this has to be a value in the z direction. All right? It has to be a value that's going either up or down from the xy plane. All right. Just like if I defined the function f of, let's say, xz, the result would be y. It would be some value y, the one variable in the 3 dimensions that has not been accounted for yet. All right. So that's something that probably people knew intuitively already, but maybe you didn't have the explicit explanation. All right. So now how do you find the domain? Well, I could put it in GeoGebra, like I said before, but I'm going to put it in as z equals, just for convenience, y equals ln negative x. I told you I'd screw it up. But the crazy part is, it's like the self-fulfilling prophecy. I didn't try to. I just knew that I'd messed something up. I accidentally hit an equal sign. I don't know. I'll just put up multiplication, ln. Indirectly, I think I kind of learned how to make a vector value function a little bit easier in 3 space, but I don't want to commit to anything there until I flesh that out. All right, so this is what the function looks like in 3 dimensions, without us having to draw it. All right, so this is what we're up against. So get a little orientation here. All right, so what this question is asking us to do is state for what values of x and or y this function exists. The short answer is, I don't have any freaking idea based on that picture. Right? I do have a sense that, okay, we're not looking at a whole heck of a lot of positive x values, if any at all. All right, we can kind of we can orient it a little. It looks like it has a little bit of a surface asymptote there. All right, it looks like the surface behaves in 3 space like an asymptote would in 2 space. And it's going downhill. It looks like it's approaching a plane rather than a line approaching, I'm sorry, a curve approaching another line. This appears to be a surface approaching a plane, but that's all I got at. I'm going to look at it analytically and say, okay, well, if I'm just focusing on the 2 factors that make this up, I got y and I got the natural log of negative x. All right, the y exists everywhere. Right, I can have all values of y. Right, so I'm not worried about that. Right, so y belongs to the set of real numbers. Right, but the natural log of x, that's the problem. Right, the natural log of negative x, I should say. And not because it's a natural log itself, but because of what's contained within the natural log. Right, you can't take the natural log or any kind of log of 0 or a negative number. So negative x has to be greater than or equal, I'm sorry, greater than 0. Right. So simplify or solve. X has to be less than 0. Divide both sides by -1. Remember, you flip the direction of the inequality. All right. So what I get from this is the domain xy, not just x anymore, such that, vertical line means such that or given that or knowing that. It's a conditional. Right? Knowing that x is less than 0 and y belongs to the set of real numbers, or you could say y is between negative infinity to infinity, but I think if we're going with this set notation, we might as well use that curved E for belongs, and then that double hatched R to represent the set of real numbers. All right, so that's the proper notation that states the domain. All right, so here you're stating the variables. And here we're stating the conditions. All right, there's a lot of familiarity there, hopefully. The thing is, in previous courses, there probably wasn't as much of an emphasis on the notation. They're like, oh, just say all real numbers. But now it's kind of important, and it's really important actually, that we state what is all real numbers, the x or the y, because it ain't both. It's one or the other, right? Sometimes it'll be both, but not in this case. If I just said all real numbers, well, that's wrong because that only applies for the y's. But for the x's, I have a significant restriction. All right. For the second problem, we have a radical in the bottom of a fraction. Same idea as back in the day. We don't want to have 0 in the bottom of a fraction. We don't want to have negative under a radical. All right. So what I can say here is that 9 minus x squared minus y squared has to be greater than 0. Now, I can try to solve this for x in terms of y. I can try to solve it for y in terms of x. It'll solve as the inequality. Not much more I can do than that. Or noting that the powers are both even and recognizing this as a conic section, right? Possibly a circle, maybe an ellipse, hyperbola. I could get it into the appropriate standard form for that conic, right? And then you'll see as we go forward, there are times and places where you would say to yourself, hey, wait a minute, is this a situation where I should go maybe into polar form? Maybe things will get easier that way. And we'll cross that bridge when we get to it, but for now we're going to work with rectangular coordinates. All right. So I want to keep the x's and y's where they are. So I'm going to bring the 9 over to the other side and make it negative. So negative x squared minus y squared greater than -9. Negate everything, including the inequality. So x squared plus y squared is less than 9. So really, anything in that circle would satisfy this equation, this multivariable equation. So it's kind of nice in that you don't have to go too crazy as long as you know your conditions. And that is the domain here is the variables x and y, the set of variables x and y, such that it follows the relation x squared plus y squared is less than 9. All right, so if you have that relation, then you're in good shape. So we can verify that using GeoGebra. Let me kill this. So z equals 1 over the square root of 9 minus x squared minus y squared. All right, so you look at it at first glance and you say, oh, it definitely seems kind of circular. So that's a win. Now let's do a top-down view. If I can get it to look. Yeah, it looks like everything is contained within a circle. Now it's a question of whether that circle is specifically x squared plus y squared equals 9. Yeah, x squared plus y equals 9, y squared. And that is the case because x squared plus y squared equals 9 has a radius of 3, and that looks like it could be a 3. Right, without getting into what the actual equation would be in 2 dimensions. No, that seems like it gets the job done. I mean, you could actually plot the cylinder if you want that gets the job done. You know, if you plot x squared plus y squared equals 9, you're like, what happened? Let me change the color here. If it'll let, oh, I gotta, you do that again. I thought it was, I'm thinking of GeoGebra. No, I'm thinking of Desmond. You see, I can't even get the names right. Nah. Settings, it's right in front of me. Mind your face, dude. It's right in front of it. All right, so x squared plus y squared equals 9. Kind of hard, it's kind of showing up there a little bit, but if I do a side view, you can see that there's a cylinder. All right, so that's a circle with infinite height. All right, so I'm putting on a little bit of a skewed angle. So this function, this multivariable function is contained within that cylinder. True? Seems to be. All right, so we're in pretty good shape. All right, now the last one here has got the most stuff, most things going on. You know, your eye is immediately drawn, I would think, to the cosine part of it, but that's actually the least relevant part, right? Because cosine functions are everywhere continuous and everywhere differentiable. So we're not, like there are no instances in which there are asymptotes or jumps or anything like that. You put a real number in, you get a real number out, right? It's the bottom that we have a problem, right? But only if x is equal to 0 and y is equal to 0. So we can't have that. So my domain here is really just that, the domain for equality squiggly bracket. xy such that x can't be equal to 0 or y can't be equal to 0. I went with an or here because if either of them are equal to 0, the function's undefined. It doesn't have to be the instance where they're both equal to 0. If either of them are equal to 0. In the other case, we needed those conditions to occur concurrently. We needed y to be part of the set of all real numbers while also x being less than 0. Here, if either of these conditions fail to be met, we have a function that does not exist. Oh, did I miss the z? Ah, I did miss the z. Thank you. Good catch. And z belongs to the set of all real numbers. So this stuff has to be true, and z belongs to the set of real numbers. All right, and that's because in the numerator, there is no value of z that would call any real value of z that would keep that cosine function from being a function that exists. All right, so thank you for that. It's the mind playing tricks on me again. Sometimes I just look at a problem and I see what I want to see. But, so we want either those two relationships to be true. X is not equal to 0 or Y is not equal to 0. And also Z belonging to the set of real numbers. So limits and continuity kind of goes hand in hand with that. But you see in the, I mean, there's a whole lot of stuff here. If you read through all of this, you're like, whoa, I got to know all this. I'll tell you right now, you already know all this. That's an oversimplification. You should know all this. You definitely know some of it. There's some things that you might have forgotten. Right? Okay, so definition of taking a math class, right? So this stuff you should definitely know. This one, yeah, I think so. I don't know that you ever had to memorize a rule to know that relation, but it always worked out. Polynomials are everywhere continuous. So if you pop a limiting constant into a polynomial, you always got something that existed as a result. You never got a d-any for that. So we're good there. Limit of a product is the product of the limit, and the limit of a quotient is the quotient of a limit. Those are a couple of big maybes. I'm not 100% sure why I have a bullet point right here, except to say I don't think I'm supposed to have a bullet point there. So that's a typo for somebody. I want bullet point crazy there. That's no good. Get rid of that bullet point. Adios. All right. So these two are the ones that are maybes. So if you have the product of two functions contained within a limit, you could find the limit of those two functions separately. Same thing with a quotient, and then divide them or multiply them accordingly. All right, the same holds true for powers, although I didn't put that there. I guess I could have. I can throw that in there. I'll take it as a typo. I don't know if I'll actually put it in, but I can just chuck it in there. So if you have something like the limit as xy approaches AB, you'll find that your least favorite part about finding limits with these kind of questions, or I'm sorry, with multivariable functions, is going to have really everything to do with writing, physically writing stuff. And so some function f of x comma y raised to the nth power, put it in brackets, is equal to same thing, eventually. This is an extension of the multiplication rule, except it's the whole limit. It's terrible looking square bracket there. Hold on, let me clean that up. The limit raised to the power. So find the limit first and then raise to the power after the fact. So powers and roots go hand in hand when it comes to this stuff. All right, so this is another rule, the additional rule. All right, that's a big one, pretty important. All right, but when you're dealing with polynomials, very easy to find limits. You just chuck the numbers in and go from there. But so, basically what that means is that you're guaranteed not to be working on problems that involve polynomials for the most part. So let's go with a rational expression here, a multivariable rational expression. Right? In some cases, you do get lucky where you can just pop in your limiting constants. So I have the x value is equal to 2. So everywhere I have an x, I'm going to replace it with a 2. The y value is approaching 1. So everywhere I have a y, I'm going to replace it with a 1. So we'd be looking at 2 times 2 squared times 1 plus 3 times 2 times 1 over 5 times 2 times 1 squared plus 3 times 1. All right. I kind of went cross-eyed in that whole experience, so there's a strong possibility I wrote something in there incorrectly. So we'll find out in a second. All right. So it's like 8 plus 6, 14. 10 plus 3, 13. 14 13ths, I think. So I'm going to Desmos it up. So I'm going to say parens. Instead of x's and y's, I'm going to use 2a squared b, a's and b's instead of x's and y's. This way it'll assume that those values are intended to be constants. And if they are, then it'll allow me to make substitutions into those constants, right? Just by adding a slider. Right, so I can just shift this over to a 2, leave that as a 1. I got 1.07, blah, blah, blah. It looks like it could be 14 13, but I can verify. Yeah, there we go. 1.0769, 1.0769. All right, so just by typing in the expression using A's and B's instead of X's and Y's, it'll create sliders. It'll allow you to create sliders, I should say, which you can toggle to whatever position you want, whatever position makes sense based on the problem, and then you can get the numerical value. And see, I just typed in the 14 over 13, but you can see you can also make a fraction out of it there. All right, so it's not too bad when it comes to evaluating multivariable functions. The problem is, if you have one where the expression, something like the practice problem below, we have, instead of x's and y's, I'm saying a's and b's. This is saying we're approaching 1, 0, so let me make that note. It says undefined. All right, now making a quick substitution and making the statement then that a limit does not exist based on getting undefined as a value, that wasn't even a good approach. That wasn't even an acceptable approach in Calc 1, because there are plenty of instances in which you get undefined on a calculator and yet the limit still exists. Right? And in fact, if I show you using direct substitution by hand, replacing all the x's with 1s, in this case it's just a 1 instance, and all the y's with 0s, I'd be looking at 0 over 1 plus 0 minus 1, which gives you 0 over 0. Now, this will come off snarky or snotty, but if you had a calc teacher who was worth anything, they told you or explained to you that this is an indeterminate, not undefined situation, right? So it's indeterminate. As in can't be determined, right? So not the answer doesn't exist. It's that we can't, based on what we have here, make a determination of whether an answer exists. And so you're probably trained to think of this as, okay, an answer can be obtained through algebra. So what it usually means is more work is required. Most of the time in Calc 1, if you got something like 1 over 0, where it's legitimately undefined, that's a case where you had to get, your knowledge of asymptotes involved and see what was going on, maybe a graph, but that's not the case here, because you spend the rest of your life trying to create this graph. I mean, look at it. Right? That honestly, that graph that I pasted in there it's a GeoGebra graph that I tweaked and moved and reoriented in the hopes that I could find the best possible viewing angle. And this is the best I can come up with. All right. If you're able to graph something like that by hand, congratulations. You're obviously really good at drawing, right? So how do we do it? Well, there's a couple of ways to handle it, but the idea is every function in 3 dimensions not only has 2 pathways to a particular point, it has infinitely many pathways to a point, right? So let's just go back here for a second to 2-dimensional math. Very simple, y equals x squared, right? If I want to find the limit as x approaches 0, all I'd have to do, and you know what I can do actually? I can actually make this slide along. Let's say f of a I'll plot the point of a comma f of a. Just so you see what the hell I'm talking about here. So I can slide my point along. Actually, I don't even need the label. If I want to approach x equals 0 from the left, pretty easy to see where I'm going. I'm going to a y value of 0. If I want to do it from the right, same idea. It's pretty easy to see where I'm going. But what if I wanted to approach it from the front or from the back or from a 20-degree angle? It's irrelevant. It's a 2-dimensional graph. All right. So then we get over into 3-dimensional space and you start looking at instances where, well, it's not just limited to coming in from the left and coming in from the right. We got all these different pathways that we can use. There is a variation of L'Hopital's rule that you can use, but if as you probably remember, L'Hopital's rule involves taking derivatives, right? So derivatives, numerator of the denominator separately, simplifying and all that good stuff. We haven't learned how to take the derivative for a multivariable function yet. So once we do that, then we'll circle back and we'll talk about L'Hopital's rule for stuff like this. Good question, though. Very good question. So in Geogebra, and I'll just put in a simple function, you know, because this is a let's not break our brains moment here. Because I already told you that this graph here is pretty crazy. Let's go with something much simpler. So y equals x squared, but in 3 dimensions. All right. So that's y equals x squared with infinite height. So if I'm looking at this, you know, the way I ordinarily would with if I can get it to have the right orientation. It's really, I guess, not that important. But now I'm kind of just wanting it to work. Almost there. Okay, there we go. So this is what the parabola would look like in 2 dimensions, but this is the parabola of infinite height. Now I start thinking about, okay, if I want to go to the origin, so if I plot 0, 0, 0, all right, and we know where 0, 0, 0 is. I just want to really accentuate it. How do I get there? Well, I could come in from the left, right? And I guess the left could be the negative x-axis. Then I could come in from the right, which I guess could be the positive x-axis. All right, but I could also come in from the negative y-axis. Okay? I can come in from the positive y-axis. I can come in from the z-axis. If you're just going along the axes, there's all these different directions that you can come in, you know, or come from, right? But I could also come in at an oblique angle, right? So I could come in, you know, starting in the upper right-hand corner, right? So I can start at you right up here where the gear thing is. I could start there and then travel down to the origin. I could start where that little house is and travel over to the origin, right? There's so many different pathways that I can take. And in fact, there's infinitely many within the subset created by this graph. So now expand that to the one that we're talking about here, which is much more disastrous, but interesting. All right. And I got to tell you, this is all stuff that we couldn't do years ago because we didn't have the ability to have a look at it. But this is what that graph is all about. To get a static image of it that looks halfway decent is just a disaster. But if you move it around and you see, it's really just kind of a blanket. You know, if you took a blanket and started folding or rolling the top end, it's like you're kind of getting into bed. You know, here's the bed, the right-hand side is the mattress, and you're just pulling the sheet back. All right. That's kind of what it looks like. All right. But what we need to do is get to the point 1, 0, comma, whatever it is, if it exists. According to this, it may or may not exist according to our analytic work, right? But if it does exist, we want to be able to figure it out, right? So long story short, theory conversation over. Let's get down to business. How do we do that? Well, what we can do is assume that we're coming in along a certain path, right? So I'm going to assume that x is equal to 1. Right? I'm going to make that assumption. Right? I'm going to assume that x is equal to 1. And I'm going to rewrite the limit. Right? So if x is equal to 1, then it's really just the limit as y approaches 0. Because x is not approaching anything anymore. X is already there. It's that 1. And I'll show you what that looks like in a second. Of y over 1 plus y minus 1. All right. Now that simplifies. So the limit as y approaches 0 of y over y. It simplifies further. I mean, you could apply the limit, but you're just going to get 0 over 0. But we do know y divided by y is equal to 1. So it's the limit as y approaches 0 of 1 that gives us a 1. All right. So we got to think about what that means. Right. Because is this our answer? Well, it can't be. That's number 1. How do we know it can't be? Show the following limit does not exist. We just got a limit to exist. So there's got to be something going on here. Let's look at x equals 1. X equals 1 is a plane. Very hard to see, but you can hopefully see that that plane intersects the surface, creating little, it's like a crossing. It creates paths everywhere where it slices through. And it kind of looks sort of rectangular. It creates those little regions. It's cutting right through like a knife through butter. Everywhere that you have that intersection between the purple and that light greenish color, that is the path created by making the assumption that x is equal to 1. And it actually kind of looks like a hyperbola. All right. So you can see that it kind of travels downward and has a little bit of a horizontal asymptote. And then on the other side, it has a horizontal asymptote and then goes vertical, or at least it seems to. All right. What we're saying is that we're traveling along that path until we get to the x value of 1. Well, we're already on the x value of 1, the y value of 0. All right. So we're looking for the moment on this plane where it intersects with a y value of 0. And what this is saying is that'll happen at this point, which I'm typing in now as 1, 0, 1. All right. So at that location, that's what the graph is approaching. All right. So what I want to know is it going to approach that point from every direction? Right. So we went along the plane, the pathway created by the intersection of the plane and the surface. So let's make the assumption that y is equal to 0. You know, go right back to scratch and assume y is equal to 0. All right, so I'm going to turn this off. I'm going to leave that point there. If we get an agreement between our results, that you're not going to like that, because if you remember going back to Calc 1, if the limit from the left and the limit from the right were the same, that was your limit. Done, got it. If they missed, if the limits did not agree, it was DNE. All right. So I call that the case of the missed high five. Right, like two freshman high school students going down the hall. All right, up top, down low. Oh, we missed. All right, and they look very foolish. All right, that's the case of the missed high five, coming in from the left, coming in from the right. All right, that we don't have that here. This would be like you're trying to high five infinitely many people. So think if you're a fan of the movie Matrix, think of the scene where Neo is being charged by all the agents all in one shot, and then he blows them all out. All right, where they're all converging on him from all the different directions. That would be a limit not existing. I'm sorry, that would be a limit existing. All right, if they all started scattering in different directions, that would be the limit not existing. All right, so that's an analogy for you, the best I got. All right, so limit, as we're assuming that y is equal to 0, which means that x is going to be approaching 1. 0 over 1 plus y. Oh, well, 1 plus, yeah, 1 plus y. I don't know if I can get myself. Minus 1. All right, so simplify limit as x approaches 1 of 0 over y. All right, now you can, why am I writing y?
Is it 0? It's x plus 0 minus 1.
Yeah, thank you. I zigged when I should have zagged. X plus 0 minus 1. All right. I accidentally was putting in the 1 for the x, and I don't even know what I was doing with the y. It was just a disaster. I got caught up with my matrix analogy. So x approaches, and I even wrote an equal sign here. This is what happens when I get excited about sci-fi. Anyway, so this would simplify to 0 over x minus 1. You don't want to substitute in yet, because we know that 0 over anything that's non-zero would be equal to 0. And so here we would get a result of 0, right? So what this is saying is if we follow the path where y is equal to 0, right, that would be, if it'll let me do it, this plane. We want to know, is it going to approach or converge on the same location? All right. We know the x values and y values are 1 and 0. The z value, the quote unquote z value that we just discovered, is supposed to be 0 for following that pathway. The 1, 0, 0, that's this point right here. They're not going to the same place. All right. So it looks like there's a little bit of a jump in the graph. All right. When that happens, that means that your limit does not exist. Right? Because it needs to converge in the same location from all directions. Right? So since there is a disagreement, the limit does not exist. So therefore, the limit does not exist. Right? Now, that's actually kind of a more of a straightforward one, because there's a lot of instances where it isn't as simple as just making the assumption that we're living in a particular plane. So that's kind of part of the fun. So let's kick over to the next page and then explore some of those cases. I just need to put this on real quick. My backup computer here. Dang it. Let's try this. Okay, so flip into the next page. we have show the following limit does not exist. A couple other cases. They get a little juicier and juicier here. All right. So we can graph it. You know, the graphs they get kind of crazy as we go, but at least until we get a good understanding of this, we definitely want to make sure that we at least investigate which type of or at least what the pathways look like depending on the assumptions that we make. All right, but this curve I think is a little easier to kind of make heads or tails of. So that's what we're going to do. We're just going to kind of rely on this curve for now. All right. Exactly. Yeah, in a case where we have 0 over 0, we calculate limits individually. Exactly. All right. So, and that's going to happen here where I replace the x's with zeros and the y's also with zeros. All right. So you do that really quickly in your head. You see that we get 0 over 0, which means that we're getting right to work now. Okay. So we'll make the assumption, assume x is equal to 0. Make our substitutions. Limit as y approaches 0, because we're assuming that x is 0. The top is just going to 0 out. The bottom, I'm replacing the x with 0. But this simplifies down really nicely, just like the previous one. 0 over y squared, which goes to 0. Now, if we're trying to show that the limit does not exist, then our goal here should be to try to get something other than 0 for another calculation. So we can assume that y is equal to 0. Not because zeros are nice numbers, but because we need to adhere, at least in the beginning, to the values that they're providing us, right? And so the limiting constants are 0. All right. So limit as x approaches 0. We're replacing all the y's with zeros. We're going to get the same thing. So now it's x squared plus 0 squared. The limit as x approaches 0 of 0 is equal to 0. So no help there. Right? So that's pretty aggravating. Right? What we need is to be able to come up with a different pathway, some kind of pathway that's actually going to help us determine a value that's going to be not 0, right? So now we got to start getting creative, right? Because we worked with plain values. We can try really anything. Sky's the limit here. It's just a matter of deciding, okay, well, do I want to work with, do I want to assume like x is 1 or -1, 20 or 5 or pi over 2 or what, you know? Do I want to make it a different function? You know, what are our possibilities here? You start looking at the nature of the rational expression, and we start thinking about, okay, well, what would happen if I was able to somehow combine the denominators? Right? Like x squared plus y squared, I can't add them together, but what if I could? That'd be pretty cool. So we have some experience with parametrics. We have a lot of experience with parametrics. Why not define a parameter that allows us to combine the denominators? That's a possibility. Right? If I replace the x's with a number that that may or may not help, and it may or may not be relevant either. It may not be something that's along the particular path. Right? But what if I say, for example, let's let x and y be some parameter t. All right. So really what I'm saying essentially is that we're going to follow a path, but we're going to follow a linear path. So this is telling us, and this might seem like it's coming out of nowhere, but it's really, there's a progression, and I'll show you. So this is going to follow a path that is linear. Because we already tried the plane route. We already tried going from the x equals 0 plane, the y equals 0 plane, looking for that intersection. But what if we just grabbed a curve in space that we knew was on the surface and went from there, right? So this linear plane is a very simple one. It's the case where x is equal to t and y is equal to t. That's a parametric equation. That corresponds with the line y equals x in 2 dimensions. All right, so when you think about a hierarchy or a progression in terms of difficulty, we usually start with the basics, like the x and y axis. Then from there, maybe you start branching out. What did we learn after we learned how to plot points, for example? You learned how to plot lines, and you learned how to plot parabolas, then other types of polynomials. Then you branched out and you got into exponentials and trig functions, things like that. They got more and more complicated. Right, so we tried the easy stuff, so let's make it a little bit more complicated, but let's not go with the most complicated thing. All right, so let's try this. What that tells me specifically is that I would have a new limit where t is approaching 0, right? Because if x and y are both defined as being equal to t, and both x and y are approaching 0, then that would necessarily mean that t would be approaching 0. Right? I can replace each of the x's and y's with t, so it becomes t times t over t squared plus t squared. Right? So, and I'll actually do this on Geogebra in a second so that you can see that I'm not just making stuff up. It's like, oh yeah, just let them be equal to each other. Why not? So you get t squared over 2t squared the t squares would cancel to a 1. The limit as t approaches 0 of the constant 1/2 would be equal to 1/2. So that's not equal to these two numbers, right? So not all pathways are bringing you to the same value. So therefore, the limit does not exist. All right, so let's look at this in Geogebra real quick. xy, so z equals, make the fraction first, xy over x squared plus y squared. All right, so that's the surface. Pretty hideous with this color. It is what it is, though. All right, look at that. Look at that catastrophe. It's pretty nasty. All right, but what I'm going to do, because we defined the path that's linear as x equals y equals t, but if we just look at y equals x, that would slice right through the plane. We know that y equals x is a linear function in 2 dimensions. I know it's hard to see, but I'm giving it a little bit of depth so you can kind of see it. The linear function in 2 dimensions, but it's specifically the one, goes through the origin, has a slope of 1, the simplest type of line that isn't a horizontal or vertical, right? So it's kind of like, well, we tried x equals 0, we tried y equals 0. Those are the most basic lines. So let's branch it out from there. So we did. That intersects with the surface and creates a path. All I'm saying is that we're following that path to the x value 0 and the y value 0. And what I'm saying here is that it's taking us to 1/2. All right, if we follow that path, this is the destination it's taking us to. Whereas all the other points, all the other paths, all the other pathways took us to the origin, right? Because not all pathways, and you can hopefully agree that the intersection of this plane, y equals x, is on the surface. We could follow this pathway. I can bring that in, mark it up a little bit, show you. I'll save it. Why not? It's a hideous color, but it's fine. Paste it in there. So what I'm saying is, regardless of the direction, we're starting off at some point over here, and we're traveling, we're walking along this path, the path created by the intersection of the plane, and it's taking us to this location. All right. All the other points, well, I'm sorry, all the other pathways are taking us to a different location. And that's the key. All right. So anyway, the next one, you can see we're kind of evolving here in terms of difficulty, but also there is a logic to it. So if you understand the logic, you're in good shape. If not, then that's what you got to work towards. All right. Well, that's the thing. If we got 0 from that computation, then we'd have to try something else, right? Which is going to bring us to the next example. So we would graduate on and on and on upward in terms of difficulty level related to functions. So after a linear function, I would try a quadratic function. After a quadratic, I would try a cubic, and then I would look for other types of relationships, and there may be a trigonometric function or something like that. All right. The thing is, because the directions in this problem, now listen, I've been known to make a typo here and there, and everywhere, but if I'm telling you that the limit doesn't exist, it doesn't exist. So you got to come up with the way in which it doesn't exist. All right. So we would not say that the limit is equal to 0. We would keep trying. We would try a different pathway. So the next example is actually going to be a good one for us to investigate, because we can try the x equals 0 pathway. So that's the limit as y approaches 0, replacing all of my x's with zeros. All right, so I get a 0 up top. I got a 0 plus y to the 4th on the bottom. That whole thing simplifies down to 0. That's poor quality 0. Let me clean that up. For a result of 0. And again, we're looking for does not exist. All right, so then I would try the pathway where y is equal to 0 to see if I get a different result. All right, I'm looking for a different value. So that would be a case where I would replace all of my y's with zeros, simplify, kind of cut to the chase here. We're going to get 0 again anyway. All right. So then it's like, all right, we go to the well one too many times, maybe. But what happens is we try it. Maybe it works, maybe it doesn't. So we're going to let x equals y equals t. Right. So that's the case where we're looking for the intersection of the plane y equals x and the surface. All right. So let's get a visual on that. All right, so this is what that surface looks like. It's got a little wonk to it. And honestly, if you kind of blur your vision a little bit, maybe not even, you kind of see like a little parabola hidden in there, right? You know, a little parabolic pathway. Hold that thought. All right. But what we're going to do is we're going to look at y equals x and follow that pathway. All right. So we've got to climb some mountains, but we'll get there. Maybe. So that would be a case where we would replace all of our x's and y's with t's. So the limit as t approaches 0 of t to the 3rd power, really, because it's t times t squared. That's going to give you t to the 3rd over t squared plus t to the 4th. And you see very quickly, you know, limit as t approaches 0. Really no help. So we know we're kind of off the path here. Oh, that should be t to the 4th. You're going to get 0 over 0. And that That's just not going to get the job done. All right. So it doesn't even give you, I mean, we could try to factor something out if you want. You factor out a t squared. You know, it'd be t over one plus t squared. At least you get something that's not 0 over 0, because 0 over 0 means you got more work to do. All right. So I knew I had to do something else. And in that case, when I plug in the 0, I'm like, oh, I did it. No, I didn't. I got 0 over 1, which is 0. All right. So no help there. All right. Or less help than I would have wanted. So what we try is we just kind of move up the ladder. And we say, all right, well, a linear function didn't work. Now you could try other types of linear functions. Maybe you're like, well, let's not give up on this linear function stuff. Yeah, maybe it's like y equals 2x or something like that. Probably not, but you know, you can give it a shot if you want. So what we can do is graduate to the next type of function, right? So the next type of function would be something like a parabolic function. It's just a question of what kind, right? So let me try y equals x squared and see if that does anything for us. Maybe. It kind of looks like the parabola is going the wrong way though, right? Like if it's going to match up with I'd like to match up with the parabolas that are already there. So maybe we do, instead of that, maybe we do x equals y squared. Yeah, that kind of seems to fit a little bit better. You know, we get a little cross section to follow that parabolic path. Try one or the other and see how it goes. But you make an observation based on the patterns that you see, and you use that to help you draw a conclusion. So I would say, let's let x equals y squared. And if we do that and define it parametrically the right way, then we'll be in good shape. So if we're going with x equals y squared, the parameters that we would use would be that x is equal to t, y would be equal to, so if I'm letting x equal to t, then y would be equal to t squared. Might actually want to go the other way, where I let y equal t, so I can let x equal t squared, right? So you could, if you want, it doesn't matter which one you let be equal to t. Yeah, I mean, you got to define your variables in some way. If I chose to let x be equal to t, then y would be the square root of t. It would still work, but you know, I don't know how much you want to work with a rat, right? So anyway, that's going to be our setup. So I can now say the limit as t, still t approaches 0, because whether x is approaching 0 or y is approaching 0, it's still going to correspond with t approaching 0. I can replace all my x's with t squares, all my y's with t's. So that's going to give me another t squared up top. Then I'm going to have if I'm replacing x with t squared, I'm going to have t squared squared. I'm going to resize that a little bit. And so here I'm getting the limit as t approaches 0 of t to the 4th over, well, t to the 4th plus t to the 4th is 2t to the 4th. Cancel, cancel. Limit as t approaches 0 of 1/2 is going to be 1/2. So if I follow this pathway where x's and y's are approaching 1s and 0s, I'm sorry, 0s and 0s, this pathway is going to take me to a 1/2. So it's going to take me to that point, which is a point that's different from the other points that we would have been brought to if we followed the 3 other paths the way it worked out. all right? So therefore the limit does not exist, but you see we had to go the extra step, all right? So if you see a surface that has a, let's say a cubic looking pattern, then you'd have to go to the next level. If you see something that looks sinusoidal, you know, looks like it has a little trig function in there, then same deal, you know? What length is that? Sorry. So now we have situations, you know, like if you look below, we're talking about the squeeze theorem. I'd like to do a quick review of that in order to kind of get us set up to be able to handle the cases that involve the squeeze theorem in multivariable senses. So, you know, it's not always the easiest thing in the world when dealing with squeeze theorem in the, you know, even in Calc 1, but it's kind of necessary, I think, to do the quick refresher. All right, so if it seems like I'm dialing it back now for a sec, there's actually a reason for that. All right, so all right, so son of a gun, I just lost my whole share. So the squeeze theorem is telling us, and I'm going to go back to Desmos real quick for this, that if you know the limit of two functions that surround another function, then you can make the assumption that the limit of the function that's trapped within those other two functions is going to take on the same limit, right, as the two outer functions. Right, so that's where we're kind of at here. So what I'm going to do is take a look at y equals, I'll write it as f of x actually, 1 over x plus 1. So that function there, y equals 1 over x plus 1, and a pretty reasonable graph. I mean, it's something that you're pretty familiar with, hopefully. Now, if I just look at that piece individually, the 1 over x plus 1, I could find the limit of that, not using a graphical approach as much as I can, or even horizontal asymptotes, as much as I can use it or determine it by saying that it has a relationship where I know that it's definitely less than some number and greater than some other number. Right, and so it's a question of what number would that be, right? So for example, I'm going to take this back to like elementary school. You know, I got the number 1/2 and I got the number 1/3, and I ask myself which one is bigger. All right, the one that has the smaller denominator is the one that's bigger, so this is the bigger number. All right, so if I can create an expression that has a smaller denominator than what I'm starting with, then I will have created a larger fraction. Right? So I can say, for example, that this 1 over x plus 1 is definitely going to be less than 1 over x. Right? Now, depending on what x is equal to, it could actually be the same as. You know, if you start getting into complex values and you start getting into the infinite, then it's possible that it could be equal. So I allow for that. Right? Now I just need something because I want to squeeze it in between two functions. And this is going out to positive infinity. I just need something that I know that 1 over x plus 1 is bigger than. Right? So what I can do, you know, I'll just type in 1 over 1 plus, or 1 over y equals 1 over x. And we'll look at it for more extreme cases here. You can see here that the purple curve is above the green curve. And, you know, it may not seem that way forever, but it is. And as you go out forever and ever and ever and ever and ever, it's always going to be above they're both going to approach 0. They're both going to have the same horizontal asymptote. If x could ever get out to infinity, it would actually get to 0, but we say that that's not something that could happen. So we keep it in the abstract sense. Now, I don't know specifically whether it's necessary to go with what I'm about to say. There might be other values, but this is what I've always done. I know that if I take this purple graph and reflect it over the x-axis, I will get something that I know is definitely going to bound the green graph on the low side. If there's another function that can be used, I've never been interested in it because this has always worked. All right, because I know that this is approaching the x-axis from the bottom side, and if it could ever get out to infinity, then that would be the only instance in which it would ever come in contact with green, but it would always be bounding the green function on the low side along the way, right? So what this tells me is that the green function is going to be trapped in between the purple and the black every step of the way, all the way to infinity. So I can now say that this inequality is true, right? So then I can say, all right, well, let's find the limit of each of the bounds. If, the copy paste function works ever. Oh, we're getting there. Conniption's coming. Find the limit of each part. All right, I'm just going to write it. Well, this one I might as well paste because I already. Knowing that I can't really find the limit of the one on the inside, in the middle, but I can find easily the limit of the functions that surround it. All right, so here I would say the limit as x approaches infinity of -1 over x, that's -1 over infinity, which goes to 0. This is 1 over positive infinity, which also goes to 0. One last copy paste job. All right. So we know that the limit as x approaches infinity of 1 over x plus 1 is in between 0 and 0. All right. If it's in between 0 and 0, then we can assume that it's equal to 0 reasonably. So I'm going to make this an equal sign now. And so that would be my conclusion. So that was an old Calc 1 problem, old Calc 1 technique. You might find it surprising that we're not going to do much of anything differently in handling this in the Calc 3 sense. All right. So that's good news. All right. So if you understood this before, but maybe like you kind of lost touch with the concept, that's fine. You're going to pick it up again. If you never knew this before, then this is a good first look at it, knowing that what we're about to do is going to support this information. All right. So the squeeze theorem in 3 dimensions. Well, it's like, look at this, out of the frying pan, right? Really not that bad, because I have this expression here of x squared y over x squared plus y squared. I just need something that I know is going to be bigger than it and smaller than it. Right? So it's kind of weird to think about it that way, but the focus is going to be really on the denominator. So actually what I'm going to do is I'm going to strip out the numerator for a second and just leave a 1 in this place. And just focus on the parent function here, 1 over x squared plus y squared. And say, okay, what number do I know that's definitely going to be larger than this? Well, some number that's going to have a smaller denominator. Smaller denominator. Right. So for example, how about 1 over, instead of x squared plus y squared, how about just 1 over x squared? All right. Because it's the sum of 2 squares. Whatever this number is going to be bigger than this number. X squared plus y squared is definitely going to be bigger than x squared. All right. Unless it gets out to infinity, which it could, but that's not relevant here. We're trying to approach 0. Now, if it gets to 0, then it might be approaching the same vertical asymptote or asymptote plane. That's fine. So we can make the assumption that there might be a location in which they'll be equal, but most of the time it's going to be the case that 1 over x squared plus y squared is going to be less than the 1 over x squared. But we could also reflect, negate, and make this a negative 1 over x squared. So now we have a relation that we know works. So then all we'd have to do is multiply this entire expression, well, really inequality, by x squared y, distribute it, and you get, when you distribute it, the middle expression back to where you started. So it'll become negative y less than or equal to x squared y over x squared plus y squared less than or equal to y. All right. So that's a relation that we know is true based on what we just did. All right. We started off with a fact that we knew was true and we built off of it from there. All right. So now I could find the limit as x, y approaches 0, 0. I'm going to do that for each part. So I'm just going to smidge some things over here. This one I smidge over, and this one I smidge. So I'm going to tuck in a limit as x, y approaches 0, 0, and get parentheses on it. And you see in all but the middle case, the x term is irrelevant. So that's going to help us figure out the limit itself. So we're getting 0 less than or equal to all of that middle stuff less than or equal to 0, which tells us that the limit of the original question has to be equal to 0. Right. So therefore, the limit's equal to 0. Yeah. So like I said, takes some doing. You get there. It's very weird and in some ways uncomfortable, but it's very doable. You just gotta kind of recall what you did in Calc 1. And honestly, I want to be fully cognizant of the fact that this is the #1 skipped topic in Calc 1. Like when people, like Calc 1 teachers are running short on time, they're like, all right, what can we cut out of the course? All right, well, first things first, let's get rid of Squeeze Theorem. And then after that, they start cutting out other things. But this is usually the first thing they do. All right. So I'm going to put a star on number 6 because I wanted to do the really easy problem and leave the really hard one for you to do. That's not really the case. It may seem that way though. Right? It's actually not really a difficult problem at all. It's just, like I said, it's just going to seem that way at first, but it's really not. I'm also going to put a star on number 7 because I remember way back when I grabbed this one from a textbook somewhere, and the textbook had arranged it where we talked about finding continuity. I'm sorry, finding domain, then finding limits, and then continuity. And then it's like, you know what? It doesn't really fit, but I'll put it in anyway. This is something that we've already kind of talked about a little bit when we got into domain. We've talked about continuity before. So you should be able to handle this, but we'll go over that one also next time. So let's hop on over to partial derivatives to give you a little taste of that this evening before you go off on your merry way. So the partial derivative concept is really sort of along the lines of what we did for limits, the idea that we're holding a variable constant, right? So we're making a statement that we're saying that, okay, this variable x is constant. Let's take the derivative in terms of y, and vice versa. One second. Right. So that's really what we're going to do. It's just the notation's a little different. How we find second derivatives is pretty different, right? Because you can't just take the derivative with respect to x and then take the derivative with respect to x again and call it a day and say that that's the second derivative, right? Because sometimes we can fluctuate back and forth between the x variable being constant and the y variable being constant, and it all has meaning. It's just a question of what that meaning is in the context of the situation. So we'll get there, but for now, we're just going to talk about notation. We're going to talk about the act of finding derivatives, and then work on it from there. All right. So you'll see here that the df dx is no longer really the classic looking d. That's the lowercase delta. Right, so we're actually kind of changing it over. That's actually the notation for a partial derivative with respect to x. So this is what we call the first order partial. With respect to x. All right, so that delta is talking about a partial derivative, but the x on the bottom is what it always has meant. That's the variable in the problem. All right, so what we do is we look at this as if y is a constant. All right, so this notation is telling us to treat y as constant. All right, so if that's the case, then I can say the partial of f with respect to x. I'm going to take the derivative of this the way I normally would, but that's the variable in the question, so it's just 6x. But this is now treated as a constant. Derivative of a constant is equal to 0. It gets a little weird when you start getting into the mixed cases where you have an expression that has both an x and a y, right? So this one here, for example, we're going to look at that as if it's negative 2y multiplied by x squared, all right? With the negative 2y being a constant multiple of the x squared, all right? And when you take a derivative, you always hang on to the constant multiple and take the derivative around it. So if you had something like 2 times the sine of x, you'd hang on to the 2, take the derivative of sine, that would become cosine, you bring the 2 back in later on. Right? So the negative 2y is a constant multiplier. We hang on to that, but then take the derivative of the x squared. That's going to become a 2x. All right. You get to a point where you do it in your head, it becomes a lot easier, but until you get the hang of it, you find yourself thinking about it a little bit more and more. All right. So then for this one, we have a 7xy squared. We're going to think of that as if it was 7y multiplied, I'm sorry, 7y squared multiplied by x. All right, so same idea when you have a constant multiple. We just hang on to it. So a positive 7y squared. But then we take the derivative of the x term. All right, derivative of x is equal to 1. Now that constant, this is the classic definition of a constant. Son of a. Derivative of constant is a 0, regardless of whether it's treated as a constant or it's a classic constant itself. All right, so clean it up. If possible, we're looking at 6x minus 4xy plus 7y squared. Why clean it up? Because we might have to take a second order partial, right? Another way of saying second derivative, but there's 4 levels of a second order partial, right? So there's basically there's basically 4 different types of second derivatives, right? So we'll get to that in a sec. Like now. Compute all 4 second order partial derivatives for this expression. By the way, I'll preemptively put a star on this page to give you a little taste of what's to come, or at least let you know what you're going to be on the hook for. So I'm going to take my first order partial here with respect to x. I'm going to make a little note of what that is, because I don't want to have to do that again. Same function. All right, so this is df dx. It's really delta f delta x, but you know it's too many syllables, so I just say d. Right. Another way of writing this, and you'll find yourself gravitating towards this more and more, is a lowercase f with a subscript of f. That means the same thing as a first order partial with respect to x for the function f. So if I use g with a subscript of f, I'm sorry, x, then I would be saying the same thing, but it would be related to a function g. All right. So it means the same thing. So what I can do is I can find the second order partial with respect to x, which is telling me just take the derivative of this again. The notation for that, there's a funky notation involving the deltas, but a nice simple notation would be f sub xx, which is just telling us to take the derivative of this function where again x is the variable and y is the constant multiplier, or just the constant, right? So everywhere where it's just a y, that's going to 0. Everywhere where y is a factor and it involves an x, then it becomes a constant multiplier, right? So this one here can be thought of, poor quality squiggly bracket, can be thought of as negative 4y times x. So when I go to differentiate here, I'm looking at 6x as a derivative of 6, negative 4y, constant multiples, we just hang on to them and take the derivative around it. The derivative of x is 1. Derivative of 7y squared is going to 0. And so we get 6 minus 4y. So that's my second order partial with respect to x. But I could also find the second order partial with respect to y, xy. Sorry, this is what we call a mixed second order partial, right? Where it's first with respect to x and then with respect to y. So I got to go back to square one here. I'm going to take my original expression so I can mark it up. You know, I'll wait the requisite 45 minutes for it to finish copying. All right, so what is considered to be a constant now is, I accidentally hit copy now, really. Is considered, what's considered to be a constant now is x, all right? Because y is what I'm differentiating with respect to. So everywhere I have an x, it is now the case So that is either a constant or a constant multiple. All right, so I'm looking at this as negative 4x times y, and I'm differentiating with respect to y. All right, so what that's going to give me, 6x goes to 0, so there's no y in it. Hang on to the constant multiple, negative 4x, y goes to 1, the derivative of 7y squared would be 14y. Clean it up. You might have to take a third order partial. Okay, so negative 4x plus 14y. All right, so that's 2 of the 4 second order partial derivatives. All right, f of xx and f of xy. Now, there's a nice rule, I'm still in my own thunder here, that tells us that if the function is continuous, which is why we talk about continuity, if the function is continuous, then the mixed second order partials will be equivalent to one another. So that tells me that f of x, f sub xy and f sub yx are actually going to be the same, because this is a continuous function because it's polynomial, right? It's got x's and y's in it, but there's no instance in which the function would not exist, right? So, but in order to actually find my first order partial with respect to y, I got to go back to square one here. So f sub y, so we start getting used to that notation, because we could say, if we wanted to, partial f with respect to y, but this is definitely a lot more concise. All right, I think that's the way we want to go. All right. So anything that's solely in terms of x is treated as a constant. All right. Anything that just contains an x, that's going to be a constant multiple. All right. So it's just a question of how you think of things. So this one is getting thought of as negative 2x squared times the y. And this one, seven x times the y squared. Right. So when I go to take the derivative of 3x squared, there's no y in it. So that goes to 0. 4y squared, there is a y in that. Take the derivative of that the way you normally would. So 8y. Hang on to any constant multiples, 2x squared. Take the derivative of y, which is 1. Hang on to any constant multiples. So positive 7x. Take the derivative of the y squared, which is 2y. And negative 9 is constant in its own right. So we just leave that, we let that go to 0. You can put a plus 0 at the end if you want. All right. So cleaning it up, 8y minus 2x squared plus 14xy. Now I need to figure out my second order partial. I already had the y with respect to y. Now I want to find it with respect to y again. All right. This one, that first term is exclusively in terms of y. So that's good. That becomes an 8. The second one is exclusively in terms of x, so that's going to 0. Really nice circumstance there. The last one, the 14x, is really thought of as a coefficient of y. So you hang on to your constant multiple, the 14x, take the derivative of just the y, which is 1, and figure out where you screwed up. Because I messed something up. Oh, no, I don't think I did. I was thinking of something else. 8 plus 14x. All right. I was for 1 second there, I thought I was on my the mixed partial. I was like, why is this not the same? So now we go to the mixed second order partial. F sub yx, which ought to be equivalent to this guy over here. All right. So they better be the same. Otherwise, I really did screw something. So now I go back to my f sub y, which is this guy. Last copy paste of the day. We're taking the derivative of this with respect to x now, which means any instance that's solely in terms of y is going to 0. Negative 2x squared, take the derivative of that the way you normally would. Negative 4x, we're on the right track here. That 14xy, we're taking the derivative of this with respect to x, which means I'm holding y constant. So I want to think of this as 14y times x. So I differentiate around the x. So hang on to the constant multiple of 14y, take the derivative of just the x, which is the 1, and I arrive at negative 4x plus 14y, which is what we got over here. So I at least know I did something right. And so that's always the plan. So you can see in number 3, it's a pretty beefy problem, which is why I didn't star a ton of questions today, because this one's going to take a little while. Compute all 4 second-order partials, which means you need the first-order partials, for cosine x sine y minus e to the xy. That e to the xy is going to throw you for a little bit of a loop, give you a little run for your money. So that's where we're going to leave it for the evening. If you have any questions, stick around. Otherwise, enjoy the rest of your evening. I'll see you on Tuesday.
Thank you, Professor.